Venturi effect and how does a carburetor work, right? So essentially, we are talking about how the carburetor would work, and the key point to notice in that would be the Venturi effect, right? So first of all, this is what a carburetor looks like, right? You must have seen this kind of structure on many engines, or even part when somebody opens up an engine and somebody talks about engines, right? This is the part that you see. Now, usually what happens is, this is the air filter. This is how it looks, right? You must have seen various types of it. You might have heard of K&N filters if you are into modification of vehicles. And this is something that, cleans the dust particles from, or avoids the dust particles to get into the engine, okay? And the other side of the Venturi, so the flow happens in this way, and the other side of the Venturi goes to the engine. The air and air mixture goes to the engine. Now, when we talk about a Venturi, there are two main aspects that come into play, right? So first one is down here, which is called the bowl. Another one is the Venturi, which is top here, right? And the same thing can be seen over here. We have the Venturi on the top, right? And then there's a bowl at the bottom, right? And after all this, there's going to be some levers and some moving things that are going to be the throttle and the choke, right? So in here you would see some valve, something like this, right? Which would be the throttle or the choke, and on the other side there'll be one or the other part, right? So again, you would have the fuel inlet from this side, right, for the bolt. And we'll be talking about this in detail. And this is the choke, right? This is the choke lever that you must have seen on many carburetors. And as you can see, this lever is choke in this case, right? Now, okay, let me go back a little bit. Yeah. So talking about the bowl itself. So initially we'll go with the bowl, okay, this part, or this bottom part. We'll be talking about this initially, right? So this is what a bowl actually looks like. Okay, so we have arrangement. So consider this, square to be the bowl, okay? And then there is the inlet from the fuel tank. So what we saw in here, this inlet, right? This is actually connected to the bowl over here from this inlet, right? Apart from that, this is the float that we have, okay? Now, if you're familiar with float, could someone tell me what exactly a float does?
Maintains the level of fuel in the carburetor bowl.
Correct, but that's what a float is doing in a carburetor. But in general, what a float does, what does this word mean? Anybody? What does float mean? It's a simple question.
Sir, a float will level the fuel.
Right? But what does
Level the
float
fuel.
mean
Whatever
in
may be the
English?
level of fuel in tank can be controlled by the float, whether to induct more fuel inside the tank. That kind of action will be taken up with the float.
It
Correct.
takes hello sir. It takes only the required amount of fuel in the storage tank, and if the level attains, it will block the fuel entering it.
Sorted. So all of you are telling me the function of float, okay, how it works in a Venturi or in a carburetor. But I'm asking you what this word means, right? It's very simple. What it is, a device that floats above a liquid, right? And you must have seen this kind of float in your flush tanks as well. In your toilets, if there's a flush tank, open the tank, you'll see one float, one ball of maybe of green color or blue color, which will float on the water. Okay, and the function of this float is to maintain the level, as most of you pointed out, to maintain the level of fuel in this bowl. Okay, so what happens is basically when the fuel is added to the chamber, it fills up to a certain point, let's say till here at this point, right? After which the float is pushed upward, it floats on this petrol, and it chokes the fuel inlet over here. So this is coming from the fuel tank, right? It chokes the fuel inlet over here so that the level is always maintained. Now let's say because of some activity and not including why this activity is there or why the fuel level is dropping. Let's say there's a drop in fuel level. In that case, the float would move downwards, right? And this opening would open up, and that's how the fuel would enter the bowl, and again the float would block the or choke the entrance of the fuel, right? So this is the basic working of float, and why this is there to maintain the fuel inside the bowl. Okay, now most of you had pointed this out, which is a good thing. Okay, now next thing is there's going to be one opening. Okay, there's going to be one opening which is Actually, let me switch to laser pointer for this. It will be better. Yeah, there's going to be one opening which is going to the venturi. Okay, and as we know, as we saw that half of this fluid is filled with half of this chamber is filled with gasoline or petrol, right? This pipe, which is opening around here, would also contain some fuel in it, right? Now, whenever there is a suction happening, okay, spoiler alert, there's going to be some suction in a venturi. Whenever there's going to be some suction, this fuel from the bottom is going to be sucked inside the venturi, okay? And since this is going to be sucked over here, we have an atmospheric opening here, okay? So why do you think we need an atmospheric opening? Could someone tell me this? Why is there an atmospheric opening over here?
If not, the liquid does not flow. Even in our building water tanks, we will have an open empty space for entering the air, passage of air.
Why is that?
Sir?
Why do we need
For
that?
the air and fuel mixture, sir.
No. For eliminating the air gap or air bubbles in between the pipelines.
Okay. For eliminating the air gap in the pipeline.
Yes, sir.
So in this pipeline.
Yes, sir.
Okay.
Even in
To
our
maintain the air pressure.
Okay. All good answers. But what it actually does is, okay, so whenever there's a suction force, okay, so let's say if there's a tank, water tank, okay, in the top of the building, and you have this tap in your kitchen tap, okay, when you open this tap, it's not the water that is flowing in here, right? Or let's put this in other words, okay, so let's say if instead of this example, let's talk about a straw. So let's say if you have this is a weird glass, let me draw a glass, right? So if you have a glass, something like this, right, which is filled with some kind of juice or coffee or whatever it is, right, and you have a straw coming out of it, right? When you suck on the straw, okay, it's not the suction force that is pulling the liquid up, okay? It's the atmospheric pressure which is pushing the liquid downwards, okay? So what happens is that in any case, the fluid would like to move, or any fluid basically would like to move from high pressure region to low pressure region, okay? So when you create a suction force inside a straw, this becomes a low pressure region, okay? And in the glass, there is atmospheric pressure acting on this, surface. And because it's being pushed downwards and there's a lesser force, lesser pressure over here, this liquid would get sucked up, okay? So it's not the suction that is providing the flow of the straw, it's actually the atmospheric pressure. Is that clear to everybody? It's slightly counterintuitive, but it can be much easier if you imagine it. Is that clear, everybody?
Yes, sir.
Yes, sir.
Sorted. So again, once more, just to brush it up once again, if you have a suction force over here, okay, it won't be the suction force that is pulling the liquid up. It's actually the atmospheric pressure which is pushing the liquid downwards, and in turn it rises into the straw to the low pressure region. Okay, so now same thing would happen over here, right? So somehow in the venturi, I'm not going to talk about right now how there is going to be the low pressure over here, but somehow there's going to be low pressure in the venturi, right? And because there's low pressure over here and there's atmospheric pressure acting on the liquid, if the liquid level is something like this, right, there'll be atmospheric pressure acting on the liquid because of this opening to the atmosphere, right? This atmospheric pressure will push the fuel upwards into the venturi, okay? And that is why we need the opening to the atmosphere. Is that clear, everybody?
Yes, sir.
Okay, so now tell me what would happen if I block this opening with my thumb.
Fuel does not go, sir.
Definitely.
Even
So yeah, what would happen if let's take our original example. Let's say if you have a glass of water and there's a straw in it, okay, and if you cap the opening of the glass such that the only thing going in is the straw, and you make it leak proof, you put seals over here around the straw, and if you try to suck the liquid, right, this liquid would not come out because there is no atmospheric pressure acting on the surface of the water. It's only on the top of the cap that you have put. So that is why we need an atmospheric opening, and as soon as you introduce this opening, it would work. It would the liquid would move upwards. Okay, you can do this experiment. Like people have done this experiment on YouTube. What you can do is take a bottle, right, a bottle cap, and do a very, very small hole into it with a very sharp object like a needle or something, right, and tightly pack the bottle, right. If you tightly pack the bottle, no liquid would fall out from this hole because there is no air entering from here, right. But as soon as you make one hole over here, the liquid would flow because there will be atmospheric air coming in. Okay, and this is what would happen if I, close the opening to the atmosphere. Okay, now we are done with the bowl part of it. Let's see how the venturi would work, right? So now going to the venturi. Okay, so what a venturi is, right? So it's a combination of convergent, throat, and divergent sections. Okay, so it's nothing. If a flow is happening, the flow will be constricted to a smaller area or smaller volume, and then that flow will be given extracted or expanded to a bigger volume. So as you can see, this area or this volume is bigger than the red volume over here, right? And again, it expands to the black volume. Okay, so if we consider the flow to be from this direction, let me take some other color for the flow. Okay, if we consider the flow to be moving from this direction, right, be it air, be it liquid, whatever it is, we can see that this liquid is going to flow like this, and it's going to be constricted to a smaller volume, and then after this is done, it will be given out to a bigger volume, something like this. Okay, so this is what a venturi is. Now, what is a venturi effect, right? So you must have seen this when you studied Bernoulli's equation. Okay, this is a very common thing that we all have studied when we see the Bernoulli's equation. So in a continuous flow, this is the keyword, continuous flow. Okay, when in a continuous flow, if the cross-sectional area is bigger, okay, the pressure would be high and the velocity would be low. Okay, in case of a smaller area like there is on the throat, the velocity would be high and the pressure would be low. Okay, so you are seeing the inverse kind of thing happening over here. The pressure is decreasing and the velocity is increasing, right? And then again, when the area increases, again in the continuous flow, the pressure will again increase and velocity will again decrease. Okay, so basically this is what happens. Now this is slightly counterintuitive when you think about it. If you have a garden hose, right? If you have a pipe attached to your garden pipe, and if you press the mouth of that pipe, okay, you will see that the water comes out at a higher pressure. You would think that, right? Because it would flow much further. But the thing is, when you introduce that opening, okay, let me draw that kind of opening over there. If I have a blank sheet, yeah. So let's go a little bit backwards, right? Something like this, yeah. So let's say if you have a pipe, right? Normally the flow is happening in this way, right? Everything is going like this, right? Now imagine if you constrict the flow of the pipe so that its area reduces to a very small point. Okay, what would happen is at this point, right, the velocity would be increased, the pressure will be decreased according to the Bernoulli's equation. That's what we saw, right? And because the velocity is increased, it will go much farther. Okay, rather than just falling somewhere around here, it would rather go like this, okay, much farther. And that's what we see. And that is not actually the pressure increasing, that's the velocity increasing. And this is what Bernoulli's equation tells us, and this is the Venturi effect. Now let's see why this happens. Okay, so I'm going to actually draw these things in terms of pressure. Okay, so blue is going to be low pressure. Okay, and let me take red is going to be high pressure. Okay, now when the initial flow is happening, right, from over here, you will see that this flow will be at higher pressure. Okay, so we have let's say P1 over here, right? Now all of these molecules are moving in a straight line till here, right? All of them are moving in a straight line. Now imagine, right, we're trying to figure out why this Venturi effect works or why this effect happens. Now imagine there's one layer which is going like this. Okay, till this point it was going straight. Now let's actually make sections over here. So this will be first section. Let's call this the second section. Let's call this the third section. Okay, and let's call this the fourth section, and this 5, and last would be 6. Okay, so probably we won't have much happening at 1 and 6, but yeah. So at second section, and section number 2, all the liquid, all the fluid molecules that are at the edge will be now pushed inwards. Correct? They'll be now pushed inwards. And because of this, all the molecules that were supposed to be over here will be slightly pushed downwards, something like this, right? And this would be a pattern. Every molecule would move inwards, something like this. and there would be one molecule which would probably just zoom straight out, but you will see this happening from all over the Venturi, something like this, right? So everything is being constricted to a smaller area. Now, what happens is with this is when this happens, let me just go to the blue layer once again. Yeah. So when this happens, more and more molecules are passing over here, right? More and more molecules are passing over here. There are hell lot of layers over here of liquid than there were in the section 1 to 2. Okay, so section 1 to 2, there were, let's say there were X amount of layers. In section 3 and 4, there will be layers more than the X amount, because in that very less space, there are more layers packed up, very closely packed up, right? And instead of talking about layer, actually, we'll not talk about layers over here, because that would be slightly confusing. Okay. Now imagine, right, within the small area, okay, within the small area of section 3 and 4, between 3 and 4, whatever fluid was here is now passing from here. All the fluid in exact number of molecules. So whatever molecules were there in 1 to 2 are now going to flow through 3 and 4. And since they cannot spread out, they are not spread out, since they are not spread out, they would have to move much faster. Correct? Is that understandable to all of you? They would have to move much faster. Is that clear?
Yes, sir.
Okay, so the fluid here is moving faster compared to what it was over here, right? Because there's less space and they have to maintain that continuous flow. So one of the molecules would push the other molecules with a much higher speed because they have to all fit in one space, right? You can imagine it as a, as a flow of people. Okay, if you constrict the flow of people, if there's a smaller road like this, right, which is converging, you would see that if there are 4 cars in this line or 3 cars in this line, ultimately there's just going to be 1 car, right? Now all of these 3 cars would compete to get into this 1 car, right? Now in traffic, in people with traffic, what happens is the flow does not increase, and that's why we have traffic jams. But in case of liquids, because there's a continuous flow, we have to maintain the continuous flow. That was the key word, remember, the continuous flow. That is what would lead to these people going much faster, okay, because they want to be here as soon as possible, okay, and that is what would increase the speed. So velocity is high, okay, when it's faster, it means velocity is high and the pressure is low. Now when we go to the other side of it, so this was the converging side, and this is the converging, and this is the diverging side of it, right? So when it goes to a diverging side, again, what would happen is now the fluid would move away from the center, right? So essentially what is happening, it's getting more space to divide up, right? It's getting more space to divide up like this, right? It's getting more places to go. The molecules can spread out more evenly, right? So again, the velocity would decrease. Over here, the velocity would decrease, okay? And the pressure would increase. Now I'm coming to why the pressure would increase and decrease, but right now you need to understand the velocity decreases, which means they want to maintain the continuous flow. That's why they go slower. Okay. Now imagine the opposite of this. If I have a convergence section, from 1 car, I need to get to 3 cars, right? So if this 1 car goes over here, there are still 2 more slots left. So this 1 car can move like this, right? The other one would move like this, and they would go in a slow speed so that when they reach over here, there's a slot for 3rd car over here, right? So while the 3rd car is coming forward, till then they would have to wait. Like if we think logically, right? That's how you can imagine it to be. But essentially what happens is the velocity decreases, okay? And then from 5 to 6 section, we'll get the initial flow that we had at P1, okay? So this P6 will be equal to P1, okay? P6 will be equal to P1. Then from P2 to P3, there will be a massive drop of pressure, which means P3 will be less than P1, okay? And P4 will be less than P5, okay? Actually, yeah, P3 would be less than P1, P4 would be less than P5, okay? And at this point, we can see that how the velocity changes. Now, why pressure changes? Okay, that's the question. So if I erase everything which is around here to get a better way to describe it, right? And yeah, so what happens is how the pressure changes, right? So let's say what can you define a pressure as? Can somebody tell me how can you define pressure? Anybody?
Force applied
per
over a
unit
unit
area.
cross-sectional area.
Okay, that's the mathematical definition for it. What do you mean by pressure when you talk about pressure? So, okay, let me give you an example. Okay, so there's one balloon. Okay, it's not inflated. Okay, you have the balloon lying over there, right? And then you inflate it. So initially the pressure inside the balloon was less, correct? Because you hadn't inflated it. Once you've inflated it, the pressure has increased. So what has changed in the balloon? What do you think?
Volume has changed.
Volume has changed. Okay, with volume,
Number of
what?
molecules.
Exactly. That's what I was looking for. Number of molecules. Okay. So when you blow up a balloon, when you inflate a balloon, what you're doing is within that small space. Okay, that's the limit a balloon can go to. You are including many more molecules, right? You have multiple molecules, and because of that, the pressure increases. So basically, how we can define pressure is the density of molecule or the population of molecule, if you will, right? And let's say if you have lower pressure, imagine there to be a balloon size of this, like it could grow up to this, but there are only 2 molecules over here. So this would result in a lower pressure, right? And this is what happens with the atmosphere. As you go away from the Earth's surface, the pressure decreases. Okay. So what basically happens is if you have Earth like this, right? The red ball is Earth, and if I draw the yellow line, the blue line, which is away from the surface, right? This blue line would result in low pressure because there'll be lesser molecules of air in the atmosphere at that level. Okay, because the gravity would pull more and more molecules towards the ground, and whatever the lighter molecules are there will move up to the blue line. Okay, and that is why as you move forward, the pressure will be, as you move away from the Earth center, the pressure will be less, right? So now that we are clear on this, that number of molecules define how much the pressure is, right? So now imagine, okay, at this point, everything is moving slower, right? Everything is moving slower. It does not have a high velocity, right? So it's going slower. When it's going slower, there are multiple or more number of molecules in one particular area. So if I take a cross section of this, right, and if I count the number of molecules in this line, at this line, right? So there'll be more number of molecules over here and then over here. Okay, because here they're constantly pushing each other and they want to be in the new position, right? So here there'll be lesser number of molecules. Okay, lesser number of molecules when compared to here, okay, at this point. So that is why the pressure decreases as the velocity increases. Okay, is that clear to everybody?
Yes, sir.
Sorted. Anybody has any doubt, please let me know. Okay, I think that is clear to everybody. Let me just erase this. Okay, so now we'll see how the air and fuel are mixed, right? So we saw the working of the bowl, right? This was the bowl. I'm not going to draw the float for now. Let's ignore the float, and we'll fill up the bowl till half with gasoline. Okay, it will be open to atmospheres from somewhere around here. Let's say there's atmospheric pressure from here, and what we'll do, we'll draw a pipe which would go out of the bowl and connect at the throat. Okay, so there's a specific reason why I've connected it to the throat. Okay, now we know the pressure in here is going to be greater than the pressure in here, right? So we know by our previous slide that P1 is going to be greater than P2. Correct? Is that clear to everybody? Okay, is that clear to everybody? Sorted. So what was P1? In case of a Venturi, in case of a carburetor, what is P1?
Atmospheric pressure.
Perfect. So this is the atmospheric pressure, right? And what is this pressure over here? It's atmospheric, right? Now P2 is going to be less than P1, which means P2 is going to be less than atmosphere. Is that true?
Yes, sir.
Correct. So now we are getting to a point where we know this pressure is less than atmospheric, which takes me to the example of our straw. There was liquid in it, there was straw, there was suction pressure, right, which was lesser than the atmospheric pressure, and there was atmospheric pressure acting on it, right? And that is why the liquid got sucked up into the straw, right? Similarly, because this pressure, the P2 pressure is less than atmosphere, this atmospheric air is going to push the liquid up into the throat. Okay? Is that clear to everybody? And that is how you're going to get fuel mixed with air. Okay, so basically what is happening with the engine? So this is what we saw the working of Venturi and bow. Now let's include engine into it. So let's say this pipe somehow goes to engine. Okay, this is the engine, and there are going to be few strokes of the engine. We know there are going to be 4 strokes, right? So the first stroke is suction, then there's compression. Could someone tell me what's the third stroke?
Power stroke and exhaust.
Power and exhaust, right? So we are interested in the suction stroke, right? We are interested in the suction stroke, which means the piston would be moving from the top to the bottom, something like this, right? Now, because it is moving like this, it's going to create a negative volume, a partial negative volume in this area, right? So it's going to create a suction force. And as you know, we have atmospheric air around here. The flow is going to move from this side to this side, correct? During the suction stroke. This is what happens in an engine. Now, when there's suction stroke going on, the air molecules will come around like this, right? Right. And let's say I'll draw the petrol with red now, okay? Just to give a clarification on it, right? Now, and I'll put a pipe connecting the Venturi to the fuel tank or a fuel float or bowl like this, right? Now, when it comes over here, when the air comes over here, right, the pressure would decrease, right? What would happen is, because the pressure is decreasing, the atmosphere will press down on the fuel and it would rise up over here, and you'll find some molecules of fuel coming out like this, okay? And from this point on, there'll be some molecules of fuel like this going into the engine, and rest of the molecules will be of air, okay? So rest of the molecules will be air, and this will be mixed within the Venturi, okay, within the carburetor. And this mixture of air and fuel will be provided to the engine, okay? Is that clear to everybody, how exactly the air is mixed with fuel? Am I audible to you guys?
Yeah. Yes, sir. Yes, sir.
Okay, is it clear to you guys how exactly the fuel is mixed with air?
Yes, sir.
Sorted. Now, the main topic of the day. What do you think happens when you press the accelerator? You know the arrangement over here. What do you think happens when you press the accelerator?
Sir, can you repeat the question, sir?
Yeah, so what is the theme of the day, right? What is the theme of today's webinar? What happens when you press the accelerator, right? What happens when you increase the throttle, rather?
Throttle getting opened wide, so that more and more air will enter to the carburetor, and so that the more pressure difference will occur, and so that largest fuel will enter by the Venturi.
Correct. So what happens is, okay, so we have 2 valves over here, right? One of this valve is called a choke, right? This is the choke valve, okay, and this is the throttle valve, okay. Now, because we will ignore choke for a while now, I'll get to how the choke works, but let's talk about the throttle valve, okay. So what engineers usually do, okay, now when we saw this example, right, in the previous slide, we saw how it would work if everything was open, if there was no restriction, okay. What we have done, we have added a restriction on this side, okay. Now, because there's a restriction, the air, when the suction force occurs at the engine side, right, there's some suction force over here at the engine side, the flow of air would be restricted by this throttle, okay. It wouldn't let the air move forward, okay. And because of that, the air and fuel mixture flowing into the engine would be less. So air and fuel mixture would be less because the throttle is in the upright position or closed position, okay. So basically what happens when you press the accelerator is the throttle turns, okay, and this turning of the throttle, this angle of turning of the throttle depends upon how much accelerator you press, right? So when you increase throttle, what exactly happens is this area increases through which the air can flow, right? And if more amount of air is flowing, right, more amount of air is flowing, which means more amount of fuel will be sucked in from the bow, right? Again, we have the fuel over here, and more amount of fuel will be sucked in. So this fuel will be more, and with respect to that, the air will also be more. Again, coming to our blue and red color scheme, right? So basically, when you increase the throttle, it's a responsive system. Okay, engine is running. You increase the throttle, more and more air and fuel get sucked into it. The engine runs faster. It requests for more fuel. it sucks fuel with higher, higher pressure, higher suction pressure, and more air gets into it, right? Now, when you leave the throttle, what happens? During that time, when you leave the throttle, when you decrease the throttle, at that time, the area is once again blocked with the air and fuel, okay, for the air and fuel to go forward. And when it is blocked, the suction, because of the suction pressure, there is less amount of air fuel going in again. And that's how the RPM of the engine decreases. Okay, is that clear to everybody?
Yes, sir.
Yes.
Sorted. So now you guys tell me what could be done. How could this throttle be improved to give you more and more? How should I put it? Yeah. So how do you think we should manage to open the throttle? Okay. So you must have seen this thing, right? When you're driving a bike, you need to turn the accelerator at a higher degree. But when you are sitting inside a car, all you need to do is press the accelerator this much. Okay, that's the angle that it goes in, right? A few degrees, right? So how much should be the turning of this throttle, right? The initial stage we saw. How much this should be turned for maximum flow?
Complete 180 degree.
Okay. Who said 180 degrees?
Not 180, sir. 90 degrees. In line.
Correct. So it should move by 90 degrees.
Yes, sir.
Okay. It should not move by 180 degree. It should move by 90 degree.
Yes,
Why
sir.
90 degree? At that point, the maximum area is opened up for the fuel to go out, air and fuel to go out, right? But if we take at anything less than that, the area is lesser. Okay. If we put the throttle something like this, the area is still lesser. Only this much area is opened up, right? So because of that, it should always move to 90 degree when it's a full throttle. Okay, so now what engineers have to do, basically there are two things that we have to do. Okay, so first of all, we need to map the throttle and the mechanism of throttle in such a way that whatever is the movement of your accelerator, right? If you're turning the accelerator on your bike, and if you're pushing the accelerator lever on your accelerator pedal on your car, right? Whatever movement is that, you need to map that movement such that the throttle movement is maximum or 90 degrees, right? And not more than that, not less than that, correct? And for that, we make mechanisms so that, when entire accelerator is pressed, complete throttle is opened. Okay, if that is not done properly, the car might not work on full efficiency, or the bike would not work, or basically the engine would not work on full efficiency. Okay, is that clear to everybody? Okay, now the next thing that we need to do is maintain a stoichiometric ratio. Have you heard of this term?
Yes, sir.
No, sir.
What does it mean?
So air fuel ratio in proper proportion.
Correct. And that proportion, the proper proportion is around 14:1, right? So 14 parts air and 1 part of fuel should be entering the engine at all times. Okay, that's the stoichiometric ratio. Now, to adjust the stoichiometric ratio, what engineers have to do, they have to design the carburetor in such a way such that the the area before the convergence, right, and the area at the throat should be in a ratio such that the pressure difference, right, which will be happening over here. So again, we have the P1, we have the P2, right? So the pressure difference should be such that it sucks a specific amount of fuel, okay, in a way that we can maintain this ratio. Okay, so let's say if 14 gram of air is entering the Venturi, right? 14 gram of air, let's say per second, is entering the Venturi. The Venturi is to be designed in a way that only 1 gram of fuel would be sucked per second. Okay, is that clear to everybody?
Yes, sir.
Yes, sir.
Sorted. So that's about the working of the throttle. That's what happens when you press the accelerator. Now, the last topic of today's discussion would be the choke. Okay. So when we talk about choke, right? Initially, what we were talking about is this valve. We were acting as if it's not even present over there, right? And have you heard of this choke value? What exactly this choke does?
Sir, it blocks the entrance of air. So only fuel rich mixture goes into the engine.
And why do we need the rich mixture?
Sir, to start that engine, initially we need to start that engine.
In in winters we use this system sir choke.
Correct. Okay. So what happens is basically, right, when you're starting the vehicle, the throttle is not much given. Okay, the throttle is not increased. So whenever you start your vehicle, it's not recommended to increase the throttle. Okay, and when you're starting in cold conditions, right, you need the engine to work with a higher fuel. Okay, you don't want to work it at stoichiometric ratio, because if it does, it wouldn't start properly, right? And for that, what we do is we close up the air inlet of the okay, air inlet of the Venturi, okay, and very small amount of air would enter from the side, something like this, right? And because again, so now if I draw the suction pressure once again from here, which is coming from the engine side, right? And if very less amount of air is entering over here, all that air should be compensated by the fuel, okay, by the fuel. It would go something like this, right? So more amount of fuel would come out, right? And instead of our stoichiometric ratio, there would be more fuel going inside the engine when compared to the air. Okay, only very few molecules of air would go in when compared to our stoichiometric ratio. Okay, and this would result in engine getting more volatile material, which is the petrol, right? So it will get higher volatile material, and it would start quicker, right? It would start quicker, and once it starts, you'll have to wait for it to get to a normal temperature, normal working temperature, and then it would give you the maximum efficiency. Okay, and that is the working of the choke. Okay, is that clear to everybody?
Yes, sir.
Sorted. Okay, so for recap, what we have seen till now, we initially saw what a carburetor looks like. We saw that there are two main sections of a carburetor. One is the bowl, one is the venturi, right? Next, we saw how the bowl works, right? We saw the float, we saw how it works, we saw the importance of opening given to it for the atmosphere. Then we saw how the venturi works, right? And what exactly happens to the venturi effect, right? I mean, we saw how the flow, is constricted to a smaller volume, how it moves faster, which results in higher velocity and lower pressure. And then we saw how this property, this venturi effect, could be used to create an air-fuel mixture so that it can be provided to an engine, right? And lastly, we saw how the throttle works, how we control this air-fuel mixture, how we increase and decrease the fuel supplied or air and fuel supplied to the engine. And then we lastly saw how to do a cold starting using a choke, right? How it works when we use a choke. So is everything clear to everybody?
Yes, sir.
Sorted. So before I go through the scholarship part, let me just open our Elite Techno Groups website. Okay, so if you're interested in learning more about these kind of things and becoming industry ready so that you can work in the industry with a much higher efficiency and to get a job basically in the industry, we have developed a nano degree, a specialization program basically. So when you go to our website, on the homepage, you'll see this kind of button. When you click on this button, you can go to vehicle dynamics course over here. It would open this kind of page. You can scroll down and see the specialization program in design CAE. Okay, the entire course is based on the vehicle dynamics part, how everything works from basics. We teach everything from scratch. You don't need to have any prerequisite knowledge of it. This course would work for around 1 year, and it has more than 6 modules, more than 11 industrial projects. Okay, you'll be working on the industrial projects. And like I said, everything is started from scratch. We tell you how everything works, why it is placed in a way it is, and how it affects the other parts. So just like we saw how the Venturi works from basic, everything else for an engine, for a vehicle, how it would be designed and how it is worked in the industry is shown in this course. And the aim of this course is to make you guys industry ready so that you can, learn and apply your knowledge in the industry and contribute to the industry, right? And like I said, it is a course for 12 months and it consists of 6+ modules such as automotive plastic design, where you will be learning how exactly the designing of plastic happens. And along with the plastic design, which is actually done in CATIA software, along with the plastic design of automotive components. So if you sit inside a car and see around you, most of the components that you would find would be plastic. Okay, most of the interior components, right? And the designing of that is very critical, right? Designing the interior components is very critical, and you will be learning those kind of modeling, those kind of designing rather. And apart from that, you will be able to design plastic components other than automotive applications, right? Similarly, we have the automotive sheet metal design module where we talk about, making the body in white of a working car, okay, which means the sheet metal body of the car. So if you see the external part or the structural part of the vehicle, it's entirely made of sheet metal in nowadays, right? So the doors, the hood, the roof, everything is made of sheet metal, and the entire structure of it. So you would be able to make that with the industrial standards. You'd be able to give the the clips, the mountings, the holes for other attachments and all those things in the sheet metal itself, and that is what industry does, right? Apart from that, you'd be able to design multiple sheet metal components apart from the automotive application, right? Lastly, you would, in the design part, you would also study the BIW fixture design. So now we have talked about the plastic design, we've talked about the sheet metal design, but when it comes to the industry, we have seen the assembly lines, right? They manufacture at a higher level or higher speed. In that case, they need automated lines and automated fixtures so that everything could be held in place and welded properly and made properly, right? For that, we make fixture. And the fixture made for BIW, so what we saw in the previous module, is made in the, is taught to made in this module. So the industry works in this way, that they give you the sheet metal components, and you need to make a fixture for it so that it could be used to assemble or help in the assembly line of these kind of components. And that is what we teach in this module, right? Apart from that, in the design part of it, you would also learn the GD&T, which is the key of almost all the design in the industry. Next, you will also learn the structural analysis, which is the FEA, right? On with using hypermesh and Ansys, where you would be checking how exactly the forces are acting on your body, and is your body strong enough to take those forces. Apart from that, you'll also learn automotive aerodynamics and thermal analysis using computational fluid dynamics. Computational fluid dynamics is nothing but the study of flow of any kind of fluid, right? Air, water, whatever it is. We study how the flow would work. We see how the flow would work, and accordingly we change our parts, right? And that is done for almost all the components in CFD. So you have your turbo machineries, your thermal analysis, your propulsion dynamics is there, and also your aerodynamics. And we focus here more on the race car aerodynamics, which is Formula One, F1 aerodynamics. And with that, you also, like I said, you initially study the race car vehicle dynamics, which give you a good idea of all the subsystems used in a vehicle, right? So just like we talked about Venturi today, there will be other subsystems like steering, suspension, transmission, chassis, brakes, and tires, and all those things which will be covered in this module. Now, the projects that you would work on would include the muscle car front bumper design, which is the plastic design of a front bumper in the car. Apart from that, you would be designing the car hood, which is of sheet metal, right? And then you would be designing also the roof, the side doors. Then you'll be designing a BIW fixture line on which the entire component will be welded and manufactured. Then you'll be doing a full frontal crash test for the simulation of your chassis. Then you'll also be working on centrifugal analysis, CFD analysis of a centrifugal pump, Formula One front wing aerodynamics analysis, and many more, right? And all of this is included in the course with lifetime access, right? And the features of the course are that we provide 5K per month guaranteed internship, industrial internship, which would last for 1 month or more than 1 month, okay, minimum 1 month. You get master degree certificate for all the modules that you've done. You get letter of recommendation from our side, internship certificate for all of the valid universities that are there who are planning to go for higher studies. Apart from that, we also help in career counseling, right? We help you make resume, we help you make LinkedIn profile, we help you for getting the job, preparing you for the interview, and we provide 100% job assistance, okay? And we also provide detailed project reports so that you can show it to your employer, and they would get a perfect idea of what you have done in this project. Now, the fees for that course is 1,20,000, but like I said, we have brought a scholarship to you guys. We don't want you to pay so much money, because like I said, we aim to upskill everybody all the engineers that are there in India, and that is why we have brought the scholarship to you. What I'll do, I'll simply paste a form in the chat box, and through that form you can apply for the scholarship. Once you fill up the form, it will give you, you will be enrolled for the scholarship, and our counselors will call you and help you with the scholarship process. And once you give the scholarship test, based on your performance, you would get a percentage discount on the initial fees. And like I said, we aim to reach out to maximum students and give them the need of the specialization program, or give them the education that is required, or fill up the gap between the industry and the students at a cheaper rate, right? Apart from our vehicle dynamics program, apart from our design specialization program, we also have programs in data science and in electric vehicles. So if you go to our website and go to the electric vehicle part of it, right, you would find a specialization in electric vehicle, which is again similar to what we have seen in design, but in the electric vehicle side of it. So if you are interested in electric vehicle, how the powertrain works, how the battery technology works, how the motor technology works, and all those things, this course is definitely for you. Apart from that, if you are interested in data science, we also have a specialization program in data science for our data science students, where we talk about data visualization, data analysis, deep learning, machine learning, artificial intelligence, and all the other stuff that comes along with the data science. So these are all the scholarship, these are all the specialization program available for you guys, and all this can be yours at a very cheaper rate. So all you have to do is register for this specialization scholarship test, and our counselor will be contacting you, guiding you as to which specialization you would go for according to your knowledge, so that you can get the maximum discount through our scholarship on our specialization program. So that's it from my end, everybody. Okay, very interesting question. Mohammed Salman is asking how the stoichiometric ratio is applied for diesel engine. So of course, the ratio is different for diesel engine. If I'm remembering correctly, it's somewhere around 21:1. I don't remember the exact value. So what is done in that? In case of diesel engine, we don't have a carburetor. Okay, we have a fuel injector. Okay, so when you accelerate, the amount of air which is entering the chamber increases. According to that, the electric system senses how much air is entering the cylinder. According to that, they provide the exact value of fuel that is required. Okay, so let's say if there is again 21 grams of air entering in the engine, or in the cylinder of the engine, the fuel injector will only inject 1 gram of jet of fuel. And that is how we maintain the stoichiometric ratio in the diesel engine.